Good morning, students. Welcome back to Digital Electronics and Logic Design online video lecture series. In continuation to the last class, I'm going to explain the various types of digital to analog converters. So we have the various types of digital to analog converters as I explained in the previous class. There are majorly three types of digital to analog converters. First one is a weighted resistor digital to analog converter, and the next one is R2 to R ladder digital to analog converter, and the next one is inverted R2 to R ladder digital to analog converter. In the previous classes, we have studied the necessity of data converters. In general, data converters are nothing but these are the integrated circuits, can be used in the digital systems to convert the one form of data into another form. So by using the data converters, we can convert the analog form of data into the digital form and the digital form of data into that we can have the two types of data converters, analog to digital converters and the digital to analog converters. If you take any digital system in the world or the digital communication, if you take any digital communication, it must involve the two converters such as analog to digital converters and the digital to analog converters. So when we wanted to process the data, when we wanted to transmit the data from source to destination, the data is in a digital form, we can transmit data with the more accuracy and the reduced noise. If the data is in the digital form, we can convert, we can transmit the data with very accurate and with the noise free from the source to destination. So that we have to convert the analog form of data into the digital form. All these basic concepts in the digital to analog converters or the analog to digital converters I have explained in the introduction of the data converters. So to have the better accuracy and the reduced noise, we have been using the data converters to transmit and to process and to store the data. So in this class, I'm going to explain the various types of digital to analog converters. In the last class, I have explained there are three types of digital to analog converters are there, such as resistor based digital to analog converter. There are three resistor based analog digital to analog converters. In short, we can call it is DAC. And all these converters we have been getting in the form of the integrated circuit such as chips only. So by using those chips, we can easily convert the analog form of data into the digital one and the digital form of data into analog form of data. So there are three types of digital to analog converters are there, such as a weighted resistor digital to analog converter, the first one. And the next one is about R2 to R ladder digital to analog converter. Anyway, in continuation to the second one, that is R2 to R ladder DAC, we will be having one more DAC that is called inverted R2 to R ladder DAC. The complete operation, opposite operation will perform on the R2 to R ladder operation, ladder digital to analog converter. So the third one will be the inverted R2 to R ladder DAC. So now I'm going to talk about the first one, that is operation of weighted resistor digital to analog converter. As I said in the previous class, it is one of the important question which has been frequently asking in the university question, university examination. So that please concentrate more on this particular fourth unit, and it is very simple and the easiest unit, so that you can score the maximum marks from this unit. So that we are going to discuss the first one, that is weighted resistor digital to analog converter. Weighted resistor digital to analog converter. So all these things we have studied. What is analog, what is digital, what is the converter, what is DAC, and all these things in the previous class only we have discussed. What is a DAC? We know that it is the digital to analog converter. It takes the digital form of data as an input, and it converts into the analog voltage or current as its output. That all these things we have studied. Digital form means the data which is there in the zeros and ones, we can call it as a digital. That will be given as an input for the digital to analog converter. Then that converter is going to convert the digital form of data into the analog one. Analog one is nothing but analog is a signal. Analog signal is nothing but it is a signal which continuously varies with respect to the time, that is called analog signal. So now this is the block diagram, or this is the process which is involved in the digital to analog converter. So general concept, all these things we have studied. The block diagram, with respect to the block diagram, everything we have studied in the previous classes. So now we have to go with the one of the few important specifications of the digital to analog converters. After going through these specifications, we have to go for the, that is weighted resistor digital to analog converter. The first specification in the digital to analog converter, that is called a resolution. Resolution is nothing but how much output can be varied, how much output can be varied for a change of the LSB in the digital input. As we know that in case of digital to analog converter, input is a digital data. In that digital data, we will find some bits that are such as binary bits, in which we can have the MSB bit and the LSB bit. MSB stands for, in the last class I have explained, most significant bit, which is having the more positional weight, and the LSB stands for least significant bit, which can have the least positional weight. So if I change the LSB bit in the input side, if I change the LSB bit in the input side, that may be 1 to 0 or 0 to 1, then what will be the change in the output? That is called a resolution. That means what? How sensitively, if the LSB is 0, then what will be the output? If LSB is 1, if I change that LSB from 0 to 1, then what is the change in the output? That is called a resolution. In other words, we can say that resolution is nothing but how much the output is sensitive with respect to the input signal. Obviously, in case of anything, output must be in significance with the input signal only. If I change the single bit of information, it has to change its outputs also. Then how much the output can be varied if I change the LSB. LSB only the bit which is having the least significant bit. And with that least significant bit, if I change the input, then what amount of output can be varied? That is called resolution. So in the resolution, we have to calculate the change of the output voltage with respect to the input signal bit information changing in the LSB. LSB stands for least significant bit. So now this is about the resolution. So now we know that if the number of bits are n, we can have the 2 power n combinations of input signals. This point also we have studied, and so that it is having the 2 power of n number of combinations, so that for every combination output is going to be changed. For every combination, output is going to be changed, because for example, I am having the three bits such as 000 to 111. 000 to 111 means 8 combinations I can have. 2 power of 3 is equals to 8 combination I can have. If I give the input is 000, I have to get one particular output as voltage, one particular voltage as output. If I change the LSB, that is 0 to 1, then the next input combination will be 001. Then it has to give the another output. Likewise, for the 2 power of n, for the 2 power of n combination, I must get the 2 power of n number of outputs. That outputs I can represent 0 to 2 power of n minus 1. 0 is also output. For example, first output I am giving all the 3 zeros. Then output will be 0 only. That is step 1, step 0. Likewise, up to 7 we can have all the output. 0 to 7 we can have. Then 0 to 7 means totally 8. Now, digital to analog converter. The next specification we can discuss, that is percentage resolution. Just now we have studied what is resolution, the change, the rate of change in the output voltage with respect to the LSB variation. That is called resolution. Then the percentage, how much that can be in resolution can be changed with respect to the, if you represent in the percentile, then that will be the percentage resolution is given as 1 by 2 power of n minus 1. Anyway, 2 power of n minus 1 is nothing but what? These are the number of outputs we can have, including the 0. 2 power of n minus 1, including 0. First step is obviously 0 only, because we will be giving all the combinations of input signals are zeros only. 0 to, and the last step is what? Last step of output will be obviously, that is 2 power of n minus 1. So percentage can be expressed, that is 1 by 2 power of n minus 1. And the next important thing in the specification, that is step size. Step size. That means what? We are having the total 8 steps, right? Then what is the variation between the steps to step? For example, in the step 1, I got the output voltage is 0. In the step 1, that is what? Step 1 we can denote with the 0. In the step 2, that is denoted with the 1. Then in step 1, if I get the output voltage is around 2 volts, then what is the step size then? 2 volts minus 0, that will be the 2. So step size can be calculated technically, that is the formula it is given as V reference. That is nothing but to earn that digital to integrate, digital to analog converter, we require to apply some V reference voltage. In the block diagram I have explained it. Step size is equals to V reference by the total number of steps. Total number of steps, we know that from 0 to the toppest step will be the 2 power of n minus 1. In technically we can call them as 8 steps only, but we are giving the names for 0. We are giving the names for each and every step. So that first step is 0 step. Second step is 1. Second step, next step is 2. And the last step will be the 2 power of n minus 1. Anyway, I will show that one in the graph also. So now I am going to have some of the problems. Example, find out the percentage resolution of digital to integrated circuit of n bits, and hence determine the value of n is equals to 2. They have given n is equals to 2. Then we have to calculate the percentage regulation. So percentage regulation formula we have 1 by 2 power of n minus 1 into 100. So this is a percentage regulation 1 by 2 power of n minus 1 into 100. And here we can have n is equals to 12, and so that we can have the value is like this. So next one is a resolution. We can go with the resolution. Resolution, we know the formula. Resolution, we have discussed. The resolution is nothing but the change in the output. Change in the output if we change the LSB bit from 0 to 1 and 1 to 0. So this table will explain the resolution examples. So formula we have, number of bits are n. If it is a 4-bit digital to analog converter, in which we can have the 4 bits. So you try to complete this one. So here n is equals to, here I am taking n, and the number of output codes, number of output codes, and the number of input combinations also, this can be 2 power of n only. For example, n is equals to 2 I am having. N is equals to 2 means I can apply the 4 combinations of input signal 0, 0, 0, 1, 1, 0 and 1, 1. For 0, 0, it will give the 1 output. For 0, 1, it will give the 1 more output. That is 1, 0, it can give 1 more, and 1, 1, that can give the 1 more output. So that means what? Based on the number of bits in the digital data, we can have the 2 power of n number of outputs at the output side of the digital to analog converter. Step size we know. If we include the 0, step size, first step is 0. We know that 0 to total number of steps will be 2 power of n minus 1. The last step name is what? 2 power of n minus 1. And the percentage regulation and the step size, everything we know. And by going with the n is equals to 10, you have to complete all this. And the next one, I am going with the applications of digital to analog converters. And I have explained very clearly, this is in the previous class. If you take any digital communication system that involves the digital to analog converters and analog to digital converters, to process the digital form of data, analog form has to be converted into the digital one. After processing the digital form of data, the processor has to give the output in the analog form again, but it can't, so that it will give the primary results in the digital form, and that digital form of data again converted into analog form, because human beings can understand only analog form of data. So all these are the best application for the digital to analog converters. Voltage controlled amplifier, digital operated attenuators, programmable filters, all these you have studied in the electronic devices, basic electronics or analog electronics. So which accept the digital data and which generates the analog form of input, because the real world completely deals with the analog one only. If you take any physical quantity in the real world, such as voltage, current, pressure, temperature, everything will vary with respect to the time. The physical quantity which varies with respect to the time, that is called analog signal. So in the real world, most of the physical quantities such as voltage, current, temperature, pressure and the time, etc. are available in the analog form, because all they vary with respect to the time. So human beings understand those particular analog signals only. But whereas digital communication, in the digital communication, whole digital system process the data in the digital form only. So some of the applications of digital to analog converters. So CD players, MP3 players and the telephones, all these are the digital to analog converters. So all these the best example for the digital to analog converters. You can go through all these things. And coming to the next one is about digital to analog converter. There are various types of digital to analog converters are there, but in the syllabus we are having only 2, such as weighted resistor digital to analog converter, and R2 to analog to digital converter. R2 to ladder type or digital to analog converter. Anyway, we are not having this multiplier digital to analog converter and non-multiplier digital to analog converters. So among all of them, we can make use effectively weighted resistor and R2 to digital to analog converter, which are very commonly used in the conversion of digital form of data into analog form. Now I am going to talk about the binary weighted resistors. So binary weighted resistor, it is one of the simplest digital to analog converter, It is the simplest digital to analog converters which uses the summing amplifier. We have studied the operational amplifier in the analog electronics. We have studied the operational amplifier in the analog electronics, and this is the operational amplifier. We are using the operational amplifier as a summing amplifier. We know that operational amplifier can make use for some of the mathematical operations such as addition, subtraction, integration, differentiation and comparison, and this is an amplifier which makes some of the mathematical operations also, so that we can call it as operational amplifier. So now this operational amplifier we have been using as a summing amplifier with the binary weighted resistor. See this one, why we call it as binary weighted resistor. Resistor value has been increasing with respect to the MSB value and LSB values. This is R, 2R, 4R and 8R. That means what? The positional weight, as the positional weight of the binary data has been increasing, the resistor value is also increasing. So that we can call it as a binary weighted resistor. So here we have been using R, 2R, 4R, 8R. That means what? As the number of bits increases, then the more number of the resistors has to be increased. So practically this is a disadvantage of the binary weighted resistor. So now we are using an inverting weighted operational amplifier. We know that operational amplifier can be operated in the two modes, such as inverting mode of operation and the non-inverting mode of operation. Now we will be using it is inverting mode. That is nothing but it is a negative terminal. To the negative terminal we are giving the input signal, whereas the non-inverting terminal, that is connected to the ground. So that now this operational amplifier is working in the inverting mode of operation. In inverting mode of operation, we will get the output is inverted with respect to the input signal, so that we will get the minus at the output side. And now it utilizes an inverting weighted op-amp circuit. Now weighted resistors are used to distinguish each bit from the most significant bit to least significant bit. This is the most significant bit and it is connected with 1R, and the next bit it is connected with the 2R, and it is the next bit is connected with 4R and the LSB. Now we took the example. Now we took the example of the 4 bit only. 1, 2, 3, 4. So that we having the wide range of resistance from the R to 8R. This is what R is nothing but what? 2 power of 0 into R. This is 2 power of 1 into R. 2 power of 2 into R. This is 2 power of 3 into R. Now all these bits, let assume that this is B0, B1, B2, B3, and we are saying it is a digital data, so that I can call it is D0, D1, D2, D3. D3 is having the more positional weight, and where D0 is having the least positional weight, and all these D0 to D3 are connected to the summing amplifier through the switches. We can call these are switches. When the switch is open, no bit is connected, so that this particular resistor will not carry any current. When this bit is 1, then this is going to make the short circuit, and so that it is connected with the reference voltage. Now that bit carries along with the reference voltage, so that the current passes through this particular resistance, so that it is going to give the input for the summing amplifier, that is inverting mode of amplifier. So the basic operation is involved in this one. Whenever the bit is 0, the switch will be open, so that that corresponding resistance will not allow any current. If the switch is closed, when the bit is 1, the switch will be closed, so that it carries the current by making use of the V reference, such that it is going to give the input signal to the amplifier, so that it is going to generate the output at the output side, that may be voltage or current. So here it has switches, such as if we are using the n bit of data, so that we have to make use the n number of switches, and these switches are called as single pole double throw switches, that is SPDT switches type. If the binary input to a particular switch is 1, it connects the resistance to the reference voltage. Just now I have explained, if the bit is 1, then only the switch will be connected through the reference voltage. It is going to carry the output, it is going to carry the current, such that it can capable of generating the output, that may be voltage or current. And if the input bit is 0, the switch connects to the resistor to the ground, so that nothing will be carried. The binary weighted resistor digital to analog converter uses an operational amplifier to sum an n bit weighted currents derived from a reference voltage. Here we will be having, this one is carrying one current, this one is carrying another, this one is carrying another current, and here onwards we will be getting the sum of the total current, and which is given as the input. So output side, what we are getting? We are getting the voltage from the Ohm's law. We can write V is equals to I into R, and here we will be having the I, and this is nothing but the R. V is equals to I into R. Total current is sigma II, that is the current through the resistor 1, 2, 3, 4, and so that we can call this current is I1, this current is I2, I3 and I4. So that I1 is nothing but, if you apply the KCL, total current is equals to I1 plus I2 plus I3 plus I4, that is the input current. So now we can have that output at the output side, that is a voltage VO is equals to, this is the output voltage. Output voltage is nothing but from the Ohm's law we can write VO is equals to I into RF. RF is nothing but, it is a feedback resistance. So this is a weighted resistors. Then I'm going to explain some basic operation which is involved this one. See. Now I am explaining only switches only. This is V reference. Now it is a V reference, and the V reference we are going to fix it one, because in order to on the integrated circuit we must apply some reference voltage, that is a V reference voltage. This is the most significant bit, and this is the least significant bit. If this is what, if this bit is applied 0, so that directly connected to the ground. If this bit is applied to the 1, so that it connected to the switch along with the reference voltage, so that it carries the current, it generates the current, so that we can have the summation of current at the inverting terminal of the summing amplifier, such as operational amplifier, so that we can get the output side such as voltage. Now we are taking the input is what? Input is 4 ones. That means what? Each one is taking a bit is, each bit is 1 only, 1, 1, 1, 1. So that now if it is 1, then these switches are closed now. These switches are closed, so that by making use of the V reference, it is going to generate the current, and that current goes through the resistance, that R. And here also this bit is also 1 now. So that if the digital data is 1, 1, 1, and that is binary form, so that its equivalent decimal will be the 15 only. We know this one. Now we are going with some of the operation involved. This one. See this one. This is what? It is a weighted resistor. Digital to analog converter. See this one, 4 bits we have given. Assume that MSB is what? MSB we have given 1101. MSB is 1, and the total bit is what? Total digital data is what? 1101. Actually this is what? 1101 in the decimal, that is the 13 only. Then we have to see that whether it is providing 13 or not. MSB, I am taking one resistance, that is 1.25 kilo ohm. 1.25 kilo ohm. this is R. Next one is what? It is 2R. This is R and this is 2R. This is 2R. This is 4R and this is about what? It is about 8R. So by choosing the first R only, we can go for the choosing of remaining 3 R's, and so that we can have, and we are choosing the feedback resistance is 10 kilo ohm, like that we can have. Now I am going with the V out. V out is equals to, what is the formula? Just now I explained from the Ohm's law. V out is equals to I into R, but this operational amplifier has been operating in the inverting mode of operation, so that we can make use, we can make use a negative symbol, so that minus I into RF is equals to minus RF, then V1 by R, V2 by R, then this is nothing but what? R. I is equals to, V out is equals to minus I into RF. RF we know that is the feedback resistance. I is nothing but I1 plus I2 plus I3 plus I4 only, and that is what? I is nothing but from the Ohm's law, V by R, V by R, V by R, and by substituting all these values we can get the value is minus 13. Minus is nothing but what? Because we have operated the operational amplifier in the inverting mode such that we got the answer is in minus. If we operate the same operational amplifier in non-inverting mode, we will get the answer is in plus 13 only. That means what? Whatever the data we have given the data in the binary form, but we got the answer is in the binary form, but we got the data is in the analog form, that is minus 13 volts. So likewise the analog digital form of data will be converted into analog form. In the next class I am going to explain about the another type of digital to analog converter, that is nothing but R2 to R ladder type digital to analog converter. Thank you students. Thank you very much.
ये क्लास आ रही थी।